Hello, everyone. Welcome back to the last talk of today. And so today we have Professor Shankar Ghosh from Tata Institute of Fundamental Research in Mumbai. And so Shankar has a very broad interest in soft matter physics experiments. But I think today he's gonna tell us a little bit about one focus is he's really interested in structures in general across different systems, such as colloids in granular systems. And I think today this talk will be about the granular system in 2D. And it's on to you.
Thank you very much. And thank you, Mahesh and Ranjini, for inviting me here. This is the first day here, and it has been a learning experience for me. Let me try and expose a particular problem, which is essentially that, okay, before I start, this work was basically done by Akash. We collaborated strongly with Jai Kumar, Paul, and Dub for this work. And this is a continuing work which has been for the last few years, still going on. And so here is this problem. So you take coins like this, and all that you want to do is you want to cover your entire surface with these coins, okay? And all these coins are identical in nature. You'd say, well, it's possible. And this is why, if all the coins are of the same shape, no problems, you can just tile it. This is the Newton's kissing problem. And you have numbers, the kissing numbers, depending upon what dimension it is. And in certain dimensions, it is known, and in certain dimensions, it's not known. But anyway, in one dimension, it is 2 dimensions is 6, and so on. So what we do is we start with this game. So just to motivate you for the problem, I start with one coin. I put the other coin around about here, and I will go along in some fashion. This is my game, so I choose what I do. So the choice is that the coin that I put next is going to touch the coin that's previously put in. Okay? So that's one choice. And I'll try and make contacts with 3 coins at least, if I can. And if I'm running short, if I make some mistakes, then at least 2. So that's what I'll do. So I try with this, third, no problem. This is all 3. Go on, go on, go on, go on, go on. I make a small mistake up there. And why did I make a mistake? Well, I am an experimentalist, and there is no computer running this thing. So I might have pushed it. How do you bring a coin up here? You push the coin, right? And there is friction down there on the plate. And maybe you have pushed it with the right force, but the friction being an indeterminate quantity, you just decided to stop it before it reached to the right position. You make a small error. And then we go on and see on. Okay, fine. You can continue with this, and you will find that styling is not getting perfect. It's kind of making many places where things just don't work around. So the hexagon that's being plotted outside is not kind of an ideal. So if you look at it, so these are the places where tiling is nice, but there are other places, for example, this is some 4 coordination, this is some 3 coordination, and you have some little polycrystalline kind of a behavior. So if you do this experiment over and over again, most likely you will end up with a polycrystal and not with a single crystal. And the reason that you have a polycrystal has nothing to do with this other things that you learn in condensed matter physics. For example, 1 dimension in structures are unstable because of thermal fluctuations. 2 dimensions are short range interactions, and 2 dimensions are unstable because of your logarithmic growth of singularities in your problem. Anyway, so here it's much more mundane. It's just because of friction. So here is this problem. The problem is that if you put in some particles up here, you get some of this structure up here. This basically, you see, there's some nice crystals up here, but then there is a lot of polycrystalline domains in the system, grain boundaries. And what is the question that is posed is, can I do something globally to this particular structure so that I can go from here to there? And I will stop here for you to ponder over this question. So here is the structure that you have, lots of defects up here, there. And I would say that what would you do to this entire structure so that you can basically generate something like this? Now remember, if I had gone here, for example, and if I asked you the same question, you'd say, well, let me try and figure out first. Maybe I'll push in a little bit this one, then I'll push in this one. But if you don't do it all perfectly correctly, then something that you do here will go up and add up something somewhere else. So it just adds up things. So it's not an easy thing to do. The other thing you could do is, why not use gravity in my problem and try and shake them up. If you shake them up, yes, you will compactify some part of it, but then you'll find that the grain boundaries will actually start moving from one point to another. So gravity shaking also doesn't really work, though one would say that, if I had a compactified structure like this, then that's the lowest energy configuration for me, and I should be able to get it, but it's very difficult to get it. So we'll do something else, and before we go or what we did in this particular experiments, I'll tell you what's the history of this particular problem. So this started off with this particular work by Paul Chaikin and his group. And what they took was, now this is, I had showed you problems in 2 dimensions. This problem is in 3 dimensions. In 3 dimensions, you pour balls into a configuration, then you don't get crystals, you get random packings of structures. So these are 3 dimensions. So they had put in balls. And what they did was they did a shear. So essentially they took the balls, sheared it like this, went back, did like this, come back. So you do this and then you go on repeating it for a large number of times. And they found that given what the friction number is and what your strain amplitude is, strain amplitude being the angle that you're twisting it by, maximum angle, you can either get a crystal or you can get a cage structures, you can get convection, that means things get mixing up in a system, or you can get a limit cycle. A limit cycle meaning that suddenly the particles have gone to a configuration such that these particles move in a very weird fashion way and come back exactly to the same place. Now, these are frictional systems. Let me give you a little fun thing about friction. The reason friction is very difficult to handle in analytical mechanics is because you can get, so analytical mechanics, what does it say you? It says that if I give you an initial conditions, your position momentum, then you know the equations of motions, you know how does it propagate in time. So you get to some particular state sometime later. And if I tell you that, you can actually retrace back the early time results. But friction tells you if I push this coin up here, it's going to come to a stop. Irrespective of what my initial configurations were, everything comes to a stop. So there is a certain degree of indeterminacy in this whole problem. I just can't use my ordinary equations of motions to basically describe something which is friction, because finally everything that comes to a stop. And remember, there is no analytical function which tells you that I can be 0 and remain 0 always. So there's something discontinuous that's going to happen there. Huh? The mu is between your particles. So in this particular system, because it's 3 dimensions, you don't have a containing walls. They're periodically going up here. So there's only particle. There's no substrate. In my problem, I have a substrate, and we'll discuss this problem. So here is what you can see. Let me run this particular picture up there.
Question. Shankar, question.
Sorry.
What does it happen at the boundary between the, can you go back?
Yeah, sorry.
Between the caged and the convection, what happens?
That's your, sorry. Yeah. So that's the cage structure, depending upon what your friction factor is here and the shear amplitude. From cage, you go into a crystal. If you are at mu and if you increase the shear amplitude, they found that from cage you go to a crystal. If you go down, you go to a limit cycle.
But if you move the other way, it's the friction coefficient and you cross the boundary between caged and convection. Right.
Between caged and convection.
Yeah.
So what is the question? What happens there?
Yes.
And again, a cage structure, what they show is that you basically have particles which do not sample the entire space. But once you have convection, actually we see convection, so you'll see what happens is particles tend to get tumbled over the entire space. It starts to move entire space. Otherwise, it's just localized over a fixed region in space. I don't remember much more than that in details. So here what you have is, remember this is a friction model and they're running it Lamb's codes. And you start tagging a particle. Just a minute, before I start, let me just stop. What you're going to see on the top is the first 10 cycles of your shear. That means the system is settling down. And then you will see the 10 cycles, but it's between 1001 and 1010. So you know, things systems have actually settled down. And the color that tells you is basically the mean square displacements of the particles. That's a trace of the particle. That's a trace of the particle. It takes one particle and it's a trajectory of the particle. So here you see the particle moving because I'm shearing it. These are all strobed images. These are non-strobed. So you find the particle. And they're kind of settling down here, but here you see that this is settled down into a very nice limit cycle. And you'd find it a little bit strange that why on the Earth would, like, you know, this kind of systems, dissipative interactions settle down into limit cycles. And what you see here is basically a strobed images. So the reason that you see these things to be not moving, because all that they're doing is when you come back here, that's the time they're taking a photograph. Every time you come back, that's the time you take a photograph. Sure. So these are not tiny displacements. These are pretty large displacements. So they are moving more of the order of a particle diameter. The maximum shear amplitude is of the order of few particle diameters. So there is a different paper now. So here we had, the way the motion was done here was basically by moving by moving these walls up here. And you can actually, now you can get a measure of that, you know, the wall here. It's pretty, or two particles there. Okay. So what you could do here is you could, instead of running through this kind of a mechanistic model, you could also run through something which is known as a stochastic models. And these are known, this model, it's not important for this talk, but these are models which were developed for ideas of random organization. The idea is if you have particles which are overlapping with each other, then move the particles in the direction which connects the diameters. Okay, doesn't matter. So, the limit cycle, the size of what? Okay, you know, this is strange because if you look at these particles, they're not really tiny motions of the particles, they're macroscopic motion of the particles. It looks to you as if, suppose you had set up a gears in your system, right? So something moves, something else moves, something else moves. So if you looked at one particle, it will do some very complicated trajectory and come back to its own position. There is no plasticity involved in the system. You could have asked that why isn't all this motion generating some plastic event? Why are the things reversible in time? Why do I see a stroke particle? That's funny because if you pose this question in terms of friction in the system, the first thing you would have expected not to have it. If at all you did expect this to have it, you'd say, well, you know, I'm kind of like throwing away my friction ideas, thinking that this is a linear system. Then what you'd have it is some very line, for example. So say, for example, you take a solid, you mark a point up here and move along this direction. The atoms do come back to its position, but you see there is no loopy character in it. So that you have a loop, and yet it comes back to its own property. In terms of friction, was a funny thing, and surprising thing. So here was this other experiment. I think this is from this year's, and what they found was that if you had lower density, then you basically land up. If you do this, and f of t is the number of active particles. Active particles means that how many times do I have to actually move these particles apart from each other? Okay. In the previous description, an active particle would be that if I move a particle and in a strobed condition, I come back exactly to its own place. Well, nothing is exact in simulations or experiments, given a tolerance for you, say 1/10 of its diameter, I say this is not an active particle. But if it doesn't come back within a 1/10 of its diameter, or whatever your choice of parameter is, that will turn out to be, you'll call it to be an active particle. And they plot this f of t as a function of time. So basically what's happening is, initially you start with lots of active particles, things just keep on moving around, and slowly they settle down into these limit cycles or whatever b may be, and your activity drops out. If you're in low density system, they find that you get a polycrystal. If you're in a high density system, you tend to get a nice crystal in the system. So this is an origin of a 2D crystal, and this is a 2D crystal, which is a system spanning 2D crystal, and no defects. Sorry.
So the nature of limit cycles must be different, because here there's a flat landscape. Once the overlaps are gone, then there's no quantified.
So here you don't have limit cycles, because you're really not talking about dynamics in such cases. There's no mechanistic dynamics in it. In the previous one, there was a mechanism. There were shear forces, equations of motions were being solved. Here it's just stochastically solved. You see two particles overlap with each other. If they are overlap with each other, then you draw a diagonal along, join the two centers of it, and just push the particles apart. And you keep on doing so that no overlaps are there in the system. And once you found that there are no overlaps in the system, it's fine. Okay, that's an absorbing state. You stop there.
And this work has no friction in it.
No, there is no friction in it. But there is no temperature in it. It's a non-Brownian system. There is thermal noise. There is thermal noise. There is some noise. No, this is not an energy minimization. This is kind of this is a process in which you are minimizing overlaps. Okay, so it's you just say, okay, if you just say that overlaps costed me energy and hence that's okay. Okay. So what they saw was, and I'll give you because it will contrast with the data that I have. So there was an f of t, this scaled at 5 minus 5 c to the power alpha, they got to be 0.42. Tau r had a divergence. Tau r is a time scale for it to go to an absorbing state. So how long did I have to wait toward an absorbing state? And you find that there's a divergence, and the number is about 1.33. People who are in SATME could recognize this is from the directed percolation class problem. Fraction of the particles which have actually reached my absorbing state, that means they're not moving any further, they kind of diverge like that, and that exponent has a 0.64. I'll contrast and compare this data. Now, in experiments, in simulations, the way that you saw was the shear was done almost like this. Actually, it was not done like that, but normally a shear would have been done. The way that you would have done a shear was you take two plates and move the top plate up.
So in the last plot, you have fraction of particle from the, so what's the starting configuration?
If this one?
No.
Some random configurations of
random
yeah.
So on the last figure, it's
this is a limit. This is a time t is equal to infinity. I've run this thing for a long time. These f of t, the fraction of particles have gone down, and at t infinity, there are really tiny values up here, right? So all these values below this particular critical point is all very tiny points. They're almost zero up here. Beyond this, you see they actually saturate to some finite value. So these are these values. That's read out these numbers from here. That's exactly this. We'll come to that question later. Let's hold on that. We just say that if let's just look at it because you can.
The color coding in the legend is confusing. So is it going into absorbing state with
No,
high packing fractions or low packing fractions?
This is all high. This is 2D. You can see this is very high packing fractions. What they've done is they've plotted the left hand side and right hand side across the transition in blue and red. This is a standard way to show that your exponent is not dependent upon which side you're approaching the transition from. So how do you apply shear? Typically, the way you apply shear would be, and that's how normally we have been taught, is this that if I take a solid like this, I pull this one up here, right? So these are area conserving. Now, the problem is we started these experiments trying to be in an area conserving geometry. Doesn't work out because your top plates tend to lose contact with your bottom plates, with your particles. So we went back to this geometry which was up here, and you look at here. This is exactly, they also haven't done this. This is not an area conserving geometry because as you're moving it across, the area is not conserved in this particular geometry. So what you do is you put in particles up here and just shear the top wall. And so there has to be some space which is open on the top. So that's our experimental idea. And what we do is we do a swing pendulum. So essentially there is one particular band up there, which is held. There are two arms like this. These are the two arms. They move like a pendulum and they move in a synchronous way. Okay? So as they move, they kind of move the particles apart. As they move here, they move the particles apart. In the process, they kind of shear down. Which particles? Okay, so look at this. The way that the pressure, the forces are being transmitted is they're transmitted by contact. So you're pushing all the particles, and that's another side. So suppose you are moving it. Now let's look at this. Okay, I'm moving this. This is this side. You're right that this arm and this arm are not the same. This arm is a pushing arm. This arm is only a confining arm. They're not doing anything because I can't, this is granular stuff. I can't pull on it, right? So all that this arm does is just provides you some kind of confinement to it. While this arm is pushing. So this arm gets pushed up. This arm, when it starts to move in, then this arm becomes a confiner and this arm becomes a pusher. Yeah. Yeah. So here the area is conserved for a very different reason because after all I've had a finite number of particles, right? Those particles are kind of conserving the area. But if you look at the area of the cell, that's not conserved. Obviously, the area of the particles, if you add them up, these particles are rigid particles and not really squishing them out. So the geometry is like this, that I start up from here. I move the walls towards one side. I come back to the center position, and then I do something like this to it. And then basically what you're doing is, as you come to the center of the particles, you take this as a reference state. You could have chosen something else. We chose this to be as a reference state. And you go through this one cycle, take a photograph here, go and tally like this, take a photograph here, and go on doing like this. Okay, and I'll say the movie, and I'll show you what really happens. You start with crystals. As time proceeds, it's kind of annealed out all the defects in your system, right? You started off with an extremely defective system. You go, let me run it again. And over time, what you saw was that the defects started getting annealed out. So if you had to plot the defect density in your system, this would be a point at which the defect density would show you a minimum. Yes.
So at the end, those two, the two holes that you end up with, they are formed pretty early in the process, right?
Yeah.
And they don't move. Did you find that surprising or?
Well, you imagine this. If this has to move out, then a lot of rearrangement of the particles have to happen.
Okay.
This kind of point defects are very difficult to anneal out in your system. If it's there, it's just, you're dead with it. Okay? And there's some other runs you may not have them, but this was a run which I chose, which had them. But if you have point defects, it's very difficult to do away with it. And remember one thing, I'm using gravity in this problem. And I'll come back to the issue of gravity.
So what are the reason why particles are arranging in this way? Why you're ending up with two holes?
Why am I? Sorry, what was the question?
So my question is what are the reason for this arrangement?
Okay.
Physically?
What is the reason for this arrangement versus say, let me go up. So let's look at why go this arrangement from here, right?
Is it less defect?
No. So remember there is a gravity in the problem. Okay. So this is important, and we'll get to the point about these experiments. This experiment has gravity, but this experiment doesn't have a gravity. So your gravity is in this direction, right? So essentially, if you go to this particular configuration where everything is like, if I put a height component to it, right, you can see that this is as it's a lower density system, your particles are larger height, the gravitational energy is higher, right? So if you go to a state like this, by removing all its defects, you're basically constantly lowering out your gravitational energy. So energetically, it would make sense that the system goes to its most compact state. So this is for an example in granular systems, you know this while you pour things in your home also. You try to pour your rice into some barrel and it's flowing, you tap it, and then the thing comes down, and you tap it more and it gets denser and denser and denser. Okay, that's some random packing, but this is a crystalline packing. So if you get to a 2D very nice ordered packing, that's the maximum density that you're going to have. So a system would tend to go there, but there are no well-prescribed routes of how to go there.
So does it depend on initial configuration, the location of these two holes?
So, these two holes. Oh, sure,
Yes.
sure. This depends upon. This is just a mic, and I chose an experiment in which I chose to show you something in which these two holes got trapped. So typically, the way we would do this experiment is, you get this structure up there, then you basically destroy the entire structure, make it flat, horizontal, and Akash destroys the entire structure, brings it back, repeat your experiments, keep on doing these experiments over and over again, right? So these are granular systems. Remember, getting high quality data statistics from here is very difficult because numbers are small. These are not like Avogadro number of particles, much smaller number of particles.
Thank you.
Okay, time scale here is it's not a parameter in this problem. One particular experiment for if the amplitude is large could take about 3 to 4 days. So you're really doing quasi-statically things. You move, you stop, take an image, move, stop, take an image, move, stop, take an image. Anything that's to do with creep time is carefully avoided in this particular problem. So the moment you introduce time in your other systems, then friction becomes a difficult problem. Everything becomes a difficult problem. So there isn't any see, there is kinematics in this problem. These are actually, okay, there are two difficulties in this problem. One is there are dynamic difficulties because once the friction goes, you don't know what the value of friction is. So sometimes it gets stuck in some positions. So there is a dynamical state to this problem. But otherwise, there is no inherent time scale is the problem. These are quasi-statically moved. So I'll tell you that, how you get to this. This is not a magic. So there's a parameter sweep, and you will see that in that parameter sweep, you will hit this point. And if you cross this point, you will not get this structure. This is a sweet spot. I just showed you, this is the best data, right? I showed you for a right parameter regime. I'll show you what happens if the parameter regime is not correct. I'll show you what happens.
Okay, why do you think, why did you get this hexagonal configuration? This is hexagonal, right?
No, this is triangular lattice. Huh? Yeah.
Yes.
Triangular, yeah.
Not a square lattice,
Well,
or not a random.
you know what
lattice.
a square lattice will do it, right? In 2D, if you have a square lattice, it's first of all, its packing is not best, and second of all, it costs you more gravitational energy. Remember, just for a fun, if I had shown you the way I was packing up here, right, randomly making errors, you did have square lattices. I think if you look at here carefully, you will find that there are some places where square lattices are there. Patches of square lattices. Typically, square lattices will not be there in the system if your system is in. But as you start getting defects, you can have gliding defects, and there you will have one exactly at the top of the other, which will basically give you a square lattice, locally a square lattice.
You mentioned vibration also, right? So under vibration, if you don't apply shear, if you do the same thing under vibration, will the phenomena be same?
No, under vibration, you will never be able to get one crystal. What will happen is constantly your defects will start to move. Okay? So because you're giving enough energy to the system, right? If that energy is enough to anneal something, energy is enough to also create a defect somewhere else. So that's why what you will basically happen is, if you can do it on you basically will see these things. You'll see, all your defect lines just moving around all over the place. You might take a snapshot somewhere where it's defectless, possible, but the next moment the defects will be generated. Okay. So that's typically what happens if you zoom in, and let's just look at this particular motion. Not sure that you can follow it, but if you let me tell you one particular thing. Remember what I said. I said my arm makes a motion which is like this. The particles, on the other hand, you will find to go up something like this, go up like that, and come back like this. It's difficult to see it, but let me again try it. If you can follow it, then it's too fast. It goes up like that, stays at some point, and then comes back. So it depends upon how you are. If you are on the right edge, the particles typically do something like that. If you're at the center, the particles, the trajectories look like an 8. If you're on this side, this and that has mirror symmetries in this. This is on the left-hand side of the image. So you have a big image, take a particle from the right-hand wall, that will look like this. If you take from the left-hand wall, it will look something like that. If you do from the center, you'll find the particles will actually do something like an H shape. Remember that that's what you would have expected if all the particles exactly follow what the plate was doing. It would have just done some kind of a sine function. So you can ask this question that, what is the amount of active particles in the system and what is now my control parameter in the problem? I've not told you what have I varied in this problem. Now let's vary one parameter in the problem. One parameter that I can vary in this problem is easily how much is the amplitude of my swing? How much am I swinging? That's an easy thing for me to vary. So we'll say that the maximum amplitude of my swing, I'll say that's to be my strain amplitude. That should be my gamma. And what I'm going to do is, these are for various values of gamma. And what I'm plotting here is number of times that I have done this cycle. So you do 1 cycle, 2 cycles. And what you measure here is, typically what you'll have is with a large number of active particles. So every time a strobe, you come back, you find none of the particles have come back. And well, 20% of the particles have come back, 30% of the particles have come back. You progressively start plotting this. So this alpha minus alpha S is for this thing is what did it go to a saturation value to? And you find that it has a decay constant to this particular process. You can now plug in the decay constant and plot it, and you'll find that this is actually a nice divergence in the system. It turns out that this divergence has an exponent which is different from the divergence that people had seen for other kinds of experiments. But remember, in those experiments, this was not phi gamma and gamma c, but this was phi and phi c. This was the density. They were plotting as a function of density. I'm plotting it as a function of gamma. Because in my systems, I really can't change my density in my system because you just put in the particles. Density is kind of evolved to. You can look at this transition. You can see that if I am below a particular critical point up here, then these loops are pretty loopy in structure and they come back almost to each other. They're like the limit cycles that I showed from Paul's paper. These are all loopy structures. These loopy structures becomes better and better as I get closer and closer to my transition point. So if I'm up here, you can see that the loopy structures are very confined. They're like very well-defined loopy structures on happening. And these are over, I think, 40, 50 cycles that I have plotted. You can see they're nice. Okay, no, these are about 20 cycles, 180 to 200. So 20 cycles. So that's the plot that you have. At the transition, this asymmetry depends upon which particle I have taken, whether it's bottom or top. Exact nature of the asymmetry, we don't know, but it's not something that I know about. If you cross the transition, then you find the particles don't really come back to its own position. What you have is then something which is like this, which is kind of the particles kind of tend to diffuse around. Right? So this is a point which goes with an absorbing transition because particles come back, the state is repeated over and over again, to a non-absorbing state up here where particles don't come back. And this is roughly the value of beta, which they had got. For us, this beta is 0.6, which is to say that how did I start losing this absorbing state? This is the development of my non-absorbing state. Now I'm not getting particles to come back to my state. And okay, I understand what you're saying. Have you found loops which close not on the first cycle, but say 10 cycles, right? No, we haven't. It's somehow we have always found the loops to close in the first cycle. We have never found periodicity greater than that of 1. That's what you N is the cycle. Okay. You can actually go up and do a Voronoi construction of these particles, find out the defects that you have in your system, and then plot the number of defects as a function of your strain amplitude. And obviously, as you increase the strain amplitude, you find that there's a sweet strain amplitude, which is 0.65, at which you have almost no defects. And this is also the strain amplitude exactly where you had the coincidence of a absorbing to a non-absorbing transition. Now, you could ask me that there is no reason why these two things have to be connected to each other, and I would agree with you that there is no reason. And I don't even claim that these two transitions are connected to each other. It could be that they're very close by. In experiments, we have not been able to. Because it's so close by in granular systems that sometimes if the transition is, there are two transitions at the same place, we won't be able to make it. You can do it as a function of density. So this is rho d minus rho s. It's kind of decays. This has almost the same form of, this is the time scale taken for your defects to be any linear system and steady state to be got. This has the same exponent that you got from the activity plot. You just push for it, and you can ask for what happens if I start looking at, if I look for my psi6 parameter, which is also an order parameter for finding out how good my crystallinity is, and that has the same exponent 0.74. By the way, there's a little technical stuff. All of you see there's some line up joining up here? Huh? Let me tell you what this line is. So when we started doing this experiment, one of the biggest problems that we had with these experiments were you couldn't use one camera for this experiment. Because what does a one camera? It's a large system. If you put one camera, you lose resolution. And second of all, remember all these objects are kind of 3D objects. As it moves toward the end, then it starts giving you the 3D view of it. Then your center detection comes into a problem. Okay? So you have multiple cameras which are basically viewing it and then stitching it out. It turns out that if you are stitching objects which have the same structure underlying it, you're stitching a bunch of coins up here and a bunch of coins up there, it's a far more difficult problem than what you have on your mobile phone stitching. Okay? The way the mobile phones work is basically it identifies certain particles, say a house here and a house there, and then stitches it. So because we have this particular problem of stitching, this stitching is actually, this is what you get here. That's like our error that we have, because in this particular thing, there were two cameras. You can go up, and if you are a stickler for details, then you say, well, I don't care about my number of size, so let me do it with 8 mm. That was with 7 mm, 9 mm, and various other sizes. And you can see that, that somehow the critical component gamma C actually scales with my diameter of the particles. Both my gamma C, and this is basically a drop in my rho density, and all of these scales with what my diameter of the particle is. So within the 3 parameter regime, so all of these takes a lot of time to do. We had 7, 8, 9. We had 3 parameters to do these experiments with. Yes. Yeah.
Then when we are applying again those large gamma, those are plane slip or the polycrystalline lines?
Grain slips.
Plane slips.
They're grain slips. They're mainly grain slips. Now, grain slips can generate now polycrystalline. It starts with the grain slips. Right? Because you're applying more than one particle, it will move over the top of the other particle, but doesn't have to lie down because now there's friction in the system. So it gets caught up there. Now, you could ask this question that why only 3 parameters, why not 5 parameters? The reason is that as you start making these particles smaller, then you have another problem. Now, nothing is 2D actually in experiments. You have, how do you make something 2D? You sandwich something between a spacers. Now, if the spacer's dimension is exactly the dimension of your particles, then all the top plate and the bottom plate friction will come into a plate. So you will have to give it a little bit of a plate. How do you cut your particles? You cut your particles through a laser cutter. A laser cutter never cuts a cylinder. It's basically because focus is, it's kind of cuts a little angle up here. Try getting this smaller and smaller, and basically the size doesn't remain any more cylindrical exactly. You see, this starts getting deformed from a cylinder. So our data with 5, you know, we tried doing pushing it, but for experimental results, we don't know what exactly is going to be. We couldn't have produced the particles with the same finesse that we could produce 7, 8, 9 particles. So you could have asked this question that what happens if I push this particle down, you know, diameter down? That's what it means right here. The critical straight diameter distance. I'll get to a point that why it is so. I said this is under gravity, and gravity plays an important role in this particular problem. And if you look at this problem, then you'll see that if I showed you this particular, now what is this? This is a state which would be a non-absorbing state form. Things don't come back. Obviously, they don't come back up here. But if I look at the bottom, which is under the pressure of all these particles, which is on the top of it, you find this is a nice. Oh, these are still absorbing particles. They do come back to their own position because they're under the weight of all the particles on the top of it. So you can now start defining a length scale in this problem. You say that that's a length scale over which the absorbing or non-absorbing transition is happening. And initially what happens is it's like a melting, you know, the top layer melts. And then as you increase the amplitude, then a little bit of the next layer melts. And as then, and the L starts to go around. And maybe if I had a very large amplitude, everything would have moved. This would not happen if gravity was not present in the problem. So what would be an absorbing state? This would be an absorbing state for you. Basically, I've plotted for you a large number of particles, and you see all of them are showing you limit cycles of some kind or the other. If you have a diffusing state, then this L, which is this from the top, where do you start getting the first limit cycles? Here you've got the limit cycles from the top. So basically that L is 0 up here. And this is the L that you have, which is greater than 0. You can, L would be an order parameter for you now to measure whether you're an absorbing or a non-absorbing transition. And you can measure this at the absorbing state L is equal to 0. And as soon as you get into an active state or a non-absorbing state, the first layer melts and then things happen. So let's ask this question that what gives me my gamma C? Okay, what gives me my critical strain? A little simple model up here. But we look at this. What you're trying, there's this gravity in this pressure. So basically there's sigma Z, which basically tells me that's the pressure that's coming onto these grains at the bottom. And this is resisting by some gamma times my elastic constant in the material. You balance both of them. And you say that, you know, when will it melt first? When the first layer fails. So L is of the order of the diameter of the particle. So L is of the order of the diameter of the particle, gamma goes to gamma C. You get that the gamma C is a linear dependence with the diameter of the particle. That's not order of magnitude estimate, and that's what we see. We don't know if you push it harder and harder to smaller dimensions, what happens. Okay. What about rotations? I told you everything comes back. Looks like things are all fine. But how do you define a particle? Now, for example, what we do with this particle is, so we have a particle like this, and we have a line like this on it. So essentially, the coordinates of the particles are xi, yi, and phi I. Phi I is an angle that this particular line, this fiducial line that I have drawn, makes with some say, horizontal line. And the problem lies here is, say I push it from the side, okay? If I push it from the side, then the particles will have to roll. But in a system that you know that if this rolls in this direction and that rolls in the opposite direction, you don't know what this guy is going to do up here. That's frustrating. So here is in this bunch of things, if I start to randomly roll particles, then there'll be a lot of frustrations in this system. So what really happens is as I start pushing these particles tend to roll. while it's all these particles, the rolling is not converted into, is transferred to these size particles. So they all translate. Now, when I do this, then these particles starts to roll and this particle starts to translate. So in this way, the rolling is never undone for. So if I had asked this question, this parameter space, did any particle come back to its original position? No, none of them came back to its original position because they developed this geometrical phase which kept on adding to itself. So the particles started doing an incessant rotation with respect to each other. So this fact that, you have, because the granular system, that I have this like a weird kind of a state in which every particle comes back to its own state is only true if I go de facto modulo over the angle of rotation. If I consider it, then none of these particles actually come back to its own position. So you can plot the angles that the particles have, and you basically will find that the particles' angles keeps on adding. And so nothing comes back to it. You can now ask for, how many minutes do I have? 5, okay. 15, okay. I'll take 5-6 minutes. So you could do the bidispersed systems. Now, why did I choose to do the bidispersed system? Because I wanted to get rid of this structural ordering in my system. If you do a bidispersed system, sorry. We didn't find big coherent patterns of rotation. This is what we found. You will find that, this is like blobs of clockwise rotating particles and anti-clockwise rotating particles. Red is clockwise, blue is anti-clockwise. They just spontaneously merge, but they do not show you large convective circuits in the system where you start getting rotations in a particular way. The phase here, this is a geometric phase. But that phase will never come back to its own position because first of all, the root is very different. But we never found out, some very, very well-defined convective loops in the system. You meant in terms of angles, or you meant in terms of particle rotation, particle positions? Yeah, no, we didn't have. We just found, these dispersed phases of reds and blues, in which the reds were moving in one direction, in the anti-clockwise direction, and the blues were all moving in the clockwise direction. And the particle which chose to move in a decided to get into a clockwise rotation, predominantly stayed in a clockwise direction. It's hardly ever you found that to go into an anti-clockwise direction. So this some slipping a lot. No, they're slipping a lot. A lot of them are slipping against each other. And the reason we did bidisperse is, and this is a story which is not yet complete, but I'll tell you what we understand from the bidisperse system. Is that that you wanted to kill the structural ordering in your system. You said that I don't want any more of that underlying crystal that happened in my system. You still get an absorbing to a non-absorbing transition in my system. You do get an absorbing to a non-absorbing transition in your system, and it's very clean. Actually, it's thanks to Akash, it's probably even cleaner data than what he has got for the crystals. Except that for some reason, this exponent now turns out to be exactly that of the dielectric percolation class. That's minus 1.33. It was minus 0.75 for your single monodispersed particles, where it had a nice packing. So the two transitions did couple to each other, or did not couple to each other, but at least happened at the same place. There, this value was about 0.75 minus 0.75. Here you get 1.33, and 1.33 is a number which if you read that as 5 minus 5c, that's the number that you'd have expected of gamma perpendicular, new perpendicular, which would be the number of minus 1.33. This number is close to, I don't know, give and take, you could also fit it to something like 0.6. This is the Manna class model that you have, alpha versus gamma. Alpha is what is the saturating value state, or the F infinity that you had for the paper which did random organization problem. It's not a fit. It's just that you just put in these numbers, you could just, the fit is not like this. The fit, you just flip it and then look on a log-log scale, which is not here. But this is not a fit. This is just like you put in the numbers and check it out what works for it. Actually, that's a good question. So, it's true that granular systems have these very, very notorious things to phase separate. If you are shaking them up, you're right that, why wouldn't they just phase separate? All the small things come to the bottom and the big things goes. You've chosen 5 and 7, and 7 and 9 size. We hadn't seen phase separation in the system, but I cannot vouch for it that, the phase separation doesn't play some underlying dynamics to it. And coming to this particular question about the fitting, actually, this is not the right way of showing it up. The right way would have been if I had plotted not from here, but on a log scale, I'd flipped it up and taken one scale. Yeah, lousy on my part.
The random organization paper, did they also report 1.8?
Yeah, they had got 1.33. Okay, so here are the data that you have for the random organization. You had 1.33. Monodispersed, we had minus 0.75. Bidispersed, probably we have 1.3. This data is still being taken, so I think we're kind of confident that we're getting into 1.3. It take lots of data to get something of that. Beta is of the order of 0.64. This is like the one class of models. We had found that to be 0.6, 0.8. I don't know how much of trust I will put into 0.8 or 0.6. Give and take, it's like the same number. These two numbers are different. And I have an inking feeling that because you had a structural transitions in the system, that absorbing to non-absorbing transition for a crystal is slightly different than what you have for a system which cannot actually crystallize. So that's coming to a conclusion. Well, it's not said. It's an interesting question to say, because people do study a lot about polydispersed systems and glassiness and things like that. Just packing of normal coins on tables, especially if you have little you make little bit errors in the system. This has far-reaching consequences than what I had just shown. It has consequences how you stitch graphs. It's a lot of things that, little small errors, how do they add up to? Why do you get polycrystalline domains? How can you get rid of these particular domains and what can you do with it? So I hope I've convinced you that even this prosaic problem of looking at coins on a table, which you thought was done and dusted, and so you never do this problem, is an interesting enough problem. Thank you. Yeah, sorry. Slides. I'll just do that. Yes. Sorry, so previous slides?
The one that I was already asking before about okay, this one. For example. Can you show pictures on the right, on the left of what you call the transition?
Of this particular system?
Yeah, for one of them. I mean, just to
very
close.
I just don't have it now here. I can show you this. I'm sure that Akash can help me. You can help me. We'll show you.
Yeah, okay. So
I'll show you.
Because the reason why I was asking, I mean, that well, you are tracing this curve, I mean, for optimizing let's say the fit, okay. But how can you be sure that it's a real transition?
How can I be sure that there is a real transition?
I mean, probably, I mean, I would say, I would like to say the picture, I mean, on the right, on the left, to see that if there is a clear signature of the two.
So one way to look at it is to look at the limit cycles. You have limit cycles on one side, you don't have limit cycles on the other. So just look at the mean square displacement versus time. That's another straight away measure for it. So that's a very good measure for it. For example, let me just look at this. Not for this one, but let me just look at this. So for example, you know that if I look at the limits, mean square displacement of all of these particles, and just look at the Stokes conditions, you'll find that those particles will actually have a finite diffusion constant. If you look for these particles, they're all on the same point. So basically, as a diffusion constant is 0. Oh, this is just one particular sample, and I'm plotting for you various particles. This is a function. This all that I'm saying is, see, there is no one transition for the entire system. What the system does is it starts to. So you start with a system like this. Yes, you start with a system like that. Okay, this is below your critical point. Everything comes back to its limit cycle. I don't know why it comes back, but it comes back to its limit cycles. You cross the transition. What really happens is the first layer starts to do something funny. So you start getting melting of the first layer. That's the layer which will show you the diffusion. So it's not that just as you go beyond that particular point, the entire system has become. So it's just some melting. Now, if you go along this particular line, this particular length that you have, that starts to grow as a function of gamma. So you basically have gamma, and up here, everything was limit cycle, so nothing, so your that length is 0. But as soon as you cross over here, then that length starts to increase, and it increases linearly as a function of my strain amplitude. Sure. Where? Sorry, there is an extra 0. Thank you very much. So that 0 is not there.
In the approach to the absorbing states, do the bottom layers get to limit cycles earlier than the top active layers?
Okay, so the limit cycle takes you. Once you get to an absorbing state, this is to do with the time taken for it to go to an absorbing state. Once you get to an absorbing state, then the limit cycle starts to happen. So for that result is this. Any of these results, for example. You could take these points up here. That takes this much time. But as you are coming closer and closer to your critical point, the dynamics are getting slower and slower. No, large number of cycles are required for you to get into.
Also, in like the glassy literature, people have been able to use these limit cycles in absorbing state to store amplitudes and memories. Can we have similar effects there, where you can read off the amplitude at which it was trained or something?
We haven't looked at it. You know what
I think the limit cycle is very unique, and there are.
So we haven't looked at the encoding memory part of it. No, we haven't. I mean, actually, yeah, I think going back to Sergio's comment that we've been trying to establish that there is a transition. And for that, we really require much more data and things like that. For the bidispersed system, I think Akash will agree that that we still don't have enough data to thump and say that we have it. Oh, the way you do it is actually almost like you kind of have a picture of it in a computer that how many particles are you putting somewhere, okay, and then you put those particles up there, give and take something of that sort, and then try to do it. Because if you just put lots of particles together and try to mix them, you will phase separate it. It's just a pain to get a bidispersed system is not an easy thing, and that's one reason why it takes so much long to do these experiments. And there's gravity in this problem. That's a bad thing. This as you identify that we can't really do with many more systems, because if I take like 2 small size particles, 2 big size particles, for example, they're quickly phase separate.
So in your bidispersed experiments, you're using particles of 2 different sizes, and you're mixing them in one single ratio, right?
Yeah, 1:1.
So what if you change that ratio? How will that affect your critical exponents?
I'll tell you what, these experiments take such a difficult thing to even, there are only very few parameter spaces where we know that they don't phase separate and things like that. If I play around with too many of these parameters, I'm sure I'll land into some other problem, which may be a phase separation. I don't want to do an experiment in which while doing the experiment, I start getting a phase separation. So even with this little parameter space, there are questions we have not answered yet. I appreciate that. I think that's a valid question to have.
What is the ratio that you're currently using?
1:1. Akash, am I right? It's 1:1.
I have a question. So talking about the effect of gravity, do you believe that if this plate was parallel to the ground, you won't have seen crystallization in the system?
I believe that if this plate was parallel to the ground, you wouldn't have been able to do the experiments. Remember, granular systems are not, you need an external field to be a stress conjugate. You have to apply pressure from the other side. And the moment you'd have crystallization in the system, the thing would have left contact with the surface. So it's shear there. It's not an easy thing. I'm not saying it's impossible. It's a difficult experiment.
No. Why I say this is because in colloidal systems, the similar effects have been seen melting as well as crystallization, as well as the transition point of strain rate. And here you are just omitting the parameter of time and considering only the increasing just the strain.
No, I think the difference is
that
there's a frictional system.
Okay.
It's not a granular. It's not a colloidal system.
Okay.
It's an entirely frictional system.
Okay.
And so in a colloidal system, you know that this is going to happen at some stage because equations will determine it. So if you look at limit cycles or reversibility is not a surprising thing in an overdamped colloidal system.
Thanks.
But if you do it, and this is a high density system, granular system with lots of friction in it. That's the reason I was telling you that all this data that I was showing you, these are little small errors that you're making due to friction, because the forcing that you do and the response that you get, there's stochasticity in it. Same force may not give you the same response. You do this, right? You take a coin and try to tilt it. The same angle doesn't cause the coin to go down every time. So sometimes it will go up and sometimes the coin goes and stops. Those kinds of stochasticity are there. Yeah, Kabir.
So you see a transition for both crystalline and amorphous structures, but what is the reason that at a particular gamma this happens in both systems? Like in the previous case in the crystals, you were able to correlate it with the most ordered state appearing at that point. So is there some analog of this ordering in the amorphous?
I don't know. I could come up with a hand-waving answer for why your gamma is dependent upon your A. That means the diameter of the particle. But to do that, I did assume kind of a structure in your system, right? That's what I did. I don't know how to think of it in a bidisperse system.
Have you measured psi 6 in this case? I mean, it would be something.
We have the coordinates. We haven't not pulled it out. We have the coordinates. We could have, but we haven't.
I see. And also, of course, gamma C depends on the friction coefficient.
Gamma C depends upon friction coefficient. Yes, gamma C does depend upon friction coefficient. Does it?
I mean, you do not expect to see these limit cycles if you have no friction.
No. So here is this question. So the way that we did this problem was that you tried to strike the whole thing from. So these were early experiments. Okay. So what you do is you look at the absorption. The fraction of active particles a function of time. What you'll see is it comes down, and suddenly you find that the entire thing goes up. And you realize that's because one particle has got stuck somewhere, and that's pushing every other particle out of the configuration that it wanted to settle down in. What you can do is you can start bumping this entire system with little hammers from the bottom. This vibration-induced lubrication. You just knock it. If you knock it, then the entire thing, then the limit cycles becomes better and better. So I do not, but remember, this is still finite friction. Finite friction and zero friction are not the same thing, right? In experiments, I don't know really how to go to that limit. I do understand zero friction means like almost Teflon light of friction, but we are still at a very high friction. We're about a 1. And if I go to 0.1, I don't know what will happen. I don't know. A Teflon, I have no idea that whether it will show you a limit cycle or not. I think it might not. I mean, it does. Okay, it does. It's experimentalist answer. It does.
Yeah. Do you have any comment about the limit cycle in the presence of any singularities?
Singularities?
Any kind of permanent defect, suppose you create. And do you have any comment over the limit cycle? What might happen, whether it is easier or difficult to happen?
I would say that there are so many defects in the entire system. I do not know if there was a particular defect. For example, I'd put in a pin, for example, somewhere, right? I think the limit cycle would still happen. It would just be avoiding the pin.
Okay.
I don't think that it would do too much to the system.
Because in normal system, your defects usually displace the change the position. That's why it might be easier to get into the limit cycle.
Yeah, I am not so sure about it, because you see, the way I think of defects in friction is also like a quenched random disorder in your system. So there, we do not think that that points of plates are moving. But Yeah, I think that if you just put in few rods here and there, the whole thing will just bypass it and then form a structure.
In one slide you showed something Voronoi analysis.
Voronoi analysis, yeah.
I didn't get what exactly you tried to get out.
Well, I
of
was
it.
basically looking at okay, so I'll tell you why I was looking at it. You could do it through Psi6 also, but okay, it's easier this way. Let's look at the Voronoi construction of it and find whether it's a 6-sided neighbor or not, the polygon is 6-sided or not. Not only that, you could have 6-sided, but you could have a distorted polygon, for example. Those kinds of things we are looking at. How good a question.
I was just thinking, do you observe something T1, T2 kind of transition throughout of that?
T1, T2. No, we have not looked for the T1, T2 transition. We share this. No.
Well, sorry, I have to stop. Well, but you can talk to Shankar.
Okay, let me give you this little thing. Why she's asking me so many questions is because the very first experiments, she had done these experiments in our lab. Okay, she's very informed. Come on, shoot down your questions.
Couple of things. Wait. Oh yeah. At any point did you see any kind of path reversibility? These are all loop reversible. The absorbing state. At any point did you see any path reversibility?
What do you mean? The same path, coming back on the same
Like
path.
if you are
No.
tracking the particles, right?
It never came back on the same path.
Okay. And you mentioned this. Most of the particles they slip, but they don't undergo rotation. How? Like I missed. What is the reason behind it? Is there a?
So if you have these particles, remember that how can two particles rotate in two different directions and third particle rotating in a particular direction if they don't start to slip? So then they're frustrated. So if you have such, patches of, it means that there's a lot of slipping in the system. So,
Is there any way of increasing the fraction of particles that are rotating?
not that I know of. Maybe to form gears and things like that, but not that way.
Just one last thing. Oh, how did you geometric phase of these particles?
Just put a Furicel line on it. Just draw a line on it. You take a center, detect the line, find the angle.
Very nice experiments.
Oh, this is the coordination number. Oh, that's like a good Z6 or a bad Z6. Like, that it's a hexagon, but it's a very distorted hexagon. And I can get you details of how we say what is a good hexagon and what is it. You look at the arms and you say how distorted are the arm lengths are. And you make some statistics out of it. You can get 6 where one of the lengths is really tiny. It's a MATLAB thing, but you could do yourself also. But the point is that you draw the Voronoi, find out the lines, and then you join the last two lines and find out how far these two lines are off from each other. And if they're like in the teeny part close to it, this is 6, but you just say that this is just like not a good 6. But if you're not, just look at the Psi6 parameter.
So you made such a big deal about how important gravity is in this experiment, and you did not vary that.
You're tilting. It's lovely if I could tilt the whole thing up.
No. You don't have to tilt it.
Then what do you do?
Do density matching. Put it in a density matching liquid.
Baba, I am doing the whole experiment dry granular system. So the whole problem is the dry granular system. The moment I put in wet systems, lubricants in your system, the whole friction game changes.
Changes, but
changes to a lot. You don't.
Question.
This is intellectual laziness.
I have a mic. You said that no particle goes back to same x, y, phi ever.
I said x, y, and phi.
Both 3 of them. Could there be any correlation over phi? Like if you plot PDF and how does it change?
What?
Of phi of all the particles? Probably distribution, yeah. Like could we expect something like that to stay there?
We haven't done.
Okay. Thank you.